Move over stationary vision. Today we're talking about motion. So thus far in the vision unit, we have talked about how we convert light into neural code, and we talked about how we perceive colors. Today we're going to be talking about how information gets from the retinal ganglion cells up to cortex and how we code for motion. So you might say we're really moving on up. This is a schematic of the visual pathway. So here's the image out in the world. It's what the person is seeing. Here are the eyes of the perceiver, and here's the brain of the perceiver. So I want to point out a few important stops on the way from eyeball to brain. So there are stops in optic chiasm. This is where some of the information from each eye crosses over to the contralateral side. There's also a stop in the thalamus. The lateral geniculate nucleus is a portion of the thalamus that's responsible for processing this visual information. And then back here in V1 is primary visual cortex, shown at the bottom. So there are a few things that I want to point out about this visual schematic. The first is that both eyes pick up input from both visual fields. So I can see stuff in the left half of space out in my left visual field with both my left eye and my right eye. There's just a tiny little slice of visual field that's coded for by only one eye. You can check this out for yourself by seeing what is way far out in peripheral vision on one side. Like, what's the farthest thing you can see out over here without moving your eyeballs. And then close your left eye, and you see that that thing is now gone, right? My right eye can't see this finger. But if I move my finger just to here, now I can see it. So the only thing in space that's coded for by only my left eye is from right here to right here. So most of visual space is coded for by both eyes. Note also that the blind spot would appear at about this point in vision. We talked a couple of class periods ago about the fact that the blind spot falls within the field of vision that both eyes can detect. So this eye's blind spot is well within the range that my right eye can see. Another thing that I want to point out here is that as we go from visual field, what's out in the world, to cortex, by the time information gets to primary visual cortex, it's clearly organized spatially. So information from the left visual field is coded in right visual cortex. But the key point here is that it's not organized by eyeball. It is not the case that everything from my left eye goes to right cortex and vice versa. The right eye is getting information from both the left and the right visual fields. And the information from the right eye about left visual field, so that's what you're seeing in blue, that part stays ipsilateral. So the information that this eye is getting about over here ends up in this part of cortex. So if you follow the red and the blue lines on the chart here, what you see is that some information from each eye stays on the ipsilateral side and some goes to the contralateral side. And what determines the side of the brain that processes the visual information is which visual field that information came from. All right, neat thing number 3 is that the visual field is not all given the same importance in cortex. So information in foveal vision, or central vision, gets more cortical space devoted to it than information out in peripheral vision. So you see the fact that in primary visual cortex there's a lot of information about like the forehead, right? It's like overrepresented, and there's less about the hair on either side. That's because the forehead is more in foveal vision, so that gets more cortical surface area. I showed the schematic earlier in class, and I just want to revisit it at this point to emphasize that importance of central foveal vision. So this is similar to the overrepresentation of areas of the body that have high acuity in somatosensory cortex, right? Foveal vision is like fingertips, and peripheral vision is like your calf. So this is one of the reasons that we have better acuity with foveal vision, because there's a more direct, even one-to-one relationship between photoreceptors and cortical neurons in V1. So from V1, from primary visual cortex, information also travels to higher order processing regions called cleverly named things like V2, V4, and V5. And they deal with things like orientation, spatial frequency, motion, color processing, and other kind of higher order, more complex visual processing. This is a now very famous schematic of the visual pathway. Every colored square is a particular brain region, and the lines between them reflect connections between those areas, so neural connections between those regions. So what I've mentioned so far is representing the retinal ganglion cells and the lateral geniculate nucleus in the thalamus and primary visual cortex V1. But as you can see, there are many other cortical processing regions involved in processing visual information, right? So this is way more information than you're responsible for, but I include it for some context and to help you appreciate the scope and complexity of the visual system. All right, so one of the quirks of the visual system that demonstrates this complexity is a condition called blindsight. People who have blindsight are in fact blind, but they're blind for a very particular reason that we'll talk about in just a minute. So they have no conscious visual experience. If you show them something and ask them what it is, they can't tell you, right? They're blind. However, they perform in an unexpected way when you give them particular types of tasks. So for instance, if you were to show someone with blindsight a picture of these two houses, and you say to them, there are two houses in front of you, which of them would you want to live in? The one on the left or the one on the right? They will say, I'm blind, I can't see them. You can say, no, just guess. I know you can't see them, but just guess. Which of these houses do you think would be nicer to live in? The one on the left or the one on the right? They'll guess the house that isn't on fire significantly more than chance. It appears that they have some perception of visual information. That is, they have access to some information about what they are not seeing, despite the fact that they don't have any conscious experience of seeing it. Here's another demonstration. So this is a man. So the man walking down the hallway has blindsight. He has no conscious experience of sight. And the researchers, the doctors that he's working with, have set up a kind of obstacle course for him in the hallway. So they tell him that he should try to walk down the hallway, but avoid any things that are in his path. And what you see is that he can do it. Despite the fact that he is blind, he can navigate around some objects in his path. So what is going on? So blindsight happens from a very specific kind of damage to the visual pathway. Blindsight can only occur when the damage is in area V1. The damage is in primary visual cortex. And yet somehow they still have this perception of the visual information, even though primary visual cortex isn't able to code for it. So the reason that this can happen is that not all information follows the main visual pathway that we just talked about, from retina, optic chiasm, lateral geniculate nucleus to V1. In fact, there's this little offshoot here that results in an alternate path that goes from superior colliculus to higher order visual processing regions like V2, V4, V5, etc. So we end up with some higher order perceptual information about the visual field, even in the absence of conscious experience of that visual input. So V1 seems to be critical for the conscious experience of visual processing, but we can have some unconscious awareness of the visual information, even if V1 is damaged, because the information is going from superior colliculus and avoiding V1 altogether to get to those higher order processing regions. All right, let's keep moving. The cortical region we're going to be focused on most today is called area V5, also called MT. It's located just a bit in front of V1, and this is the portion of the visual system that is most heavily implicated in motion processing. How do we know it's for motion processing? Well, one reason is that if we put people in an fMRI, we see activity in V5 when they're viewing things that are moving, but not when they're viewing things that are standing still, not when they're viewing still images. So this suggests that it's not just for processing visual information generally, rather it's specifically for processing information about motion. Another way that we know V5 is important for motion processing is that if people have damage to V5, they develop a condition called a kinetopsia. Some people have called this motion blindness. So if damage to V5 happens, and this can either happen via a stroke or some kind of traumatic brain injury, people experience visual information as seeing a series of still frames rather than seeing motion. So what does this look like? Imagine going to a dance club and seeing a strobe light flashing every few seconds, right? All you see is snapshots, but you don't see continuous motion between them. So that is one of the ways that people with a kinetopsia have described the condition. In one account of a kinetopsia, a patient reportedly had difficulty pouring tea because the liquid appeared frozen like a glacier, and she was unable to tell when the liquid had risen to the correct level in the teacup, and suddenly it had overflowed. She had trouble following conversations because she couldn't see face and mouth movements. And she had difficulty crossing the street because she couldn't judge how quickly things were coming. She couldn't judge the speed of cars. Cars looked really far away and then suddenly were very close. So our ability to connect frames of motion together is really important for making sense of a complicated moving world. V5 is organized in a really fascinating way. If we zoom in on a little chunk of V5, so here's a little chunk of cortex, there are columns of cortical tissue arranged in V5 that respond selectively to different directions of motion. So the neurons here would fire when something moves to the left, but not when something moves to the right. So we've got another example of a way that information about different sensory qualities is organized in physical space in the brain, right? We've talked about gustotopic maps in which one of the ways we know which tastants are present is that different regions of gustatory cortex are more activated for some tastants than others. We've talked about the fact that we know what pitches are present because different regions of auditory cortex code for different pitch. We've talked about how we know where on the body is being touched because different regions in somatosensory cortex are active. And now we've got the same thing for visual processing with motion. We have specific cortical neurons that respond to one direction of motion and different cortical neurons that respond to different directions of motion. So using population coding, using the simultaneous input from all of these different direction selective columns of neurons, we can make sense of how things are or aren't moving in our visual field. So, for instance, if you are looking at something that is not moving, if you're looking at a still image, you're going to have balanced activity in all of the different columns of V5. So they're all going to be firing at their baseline firing rate. They're all just saying, yep, no, nothing leftward. Anything rightward? Nope, nothing rightward. All right, so they're just, firing at baseline. But if you have more activity in one of those direction selective columns in V5, that indicates that there is motion in one particular direction. All right, so this system for coding for motion can lead to some really incredible visual phenomena. I'm going to play a visual demonstration next that involves some flashing lights and motion. If you have any photosensitivity and prefer not to be exposed to a strobe-like motion, simply forward the video to the next marker, which is at timestamp
13:18.
All right, so what I want you to do is stare at the center of the screen. Try not to move your eyes or your head, just keep staring. Keep staring. Keep staring. All right, keep looking at the same place, and without moving your eyes, lift one of your hands up so it is close to your field of view. Keep staring. Now look at your hand. Whoa! What's happening? I'm going to make you wait until class and figure out what's happening in the problem set. What a cliffhanger. All right, so going back to the organization of V5, how can it be that these neurons know what direction of motion is present? They're just getting input from, retinal ganglion cells, and the retinal ganglion cells can only say, there is something there is something there, but they can't determine whether things are moving. So how do the neurons in V5 know that there's motion? As you read, the way that this is achieved is that cells in V5 are wired up with what are called delay gates between the retinal ganglion cells and the cells in V5. So cells in V5 only fire when activity happens in both the A pathway and the B pathway simultaneously, such that those signals reach what's marked X here at the same time. So that means that the cell in V5 will only fire when a short time has passed since retinal ganglion cell A fired and retinal ganglion B fired at the same time. So let's work through an example of that. Let's work through an example of this. All right, so let's say a ladybug appears out in the visual field. It's going to stimulate a certain patch of photoreceptors that are going to stimulate a particular retinal ganglion cell that codes for that region of the visual field. So the photoreceptors become activated, the retinal ganglion cell fires. The action potentials from that retinal ganglion cell then synapse on the delay gate, shown as D. But the ladybug is on the move, so it moves to the receptive field of a different retinal ganglion cell, causing that retinal ganglion cell to become activated. Now, if retinal ganglion cell B becomes activated at about the same time that the signals from retinal ganglion cell A reach retinal ganglion cells A's delay gate, that means that information from both the A pathway and the B pathway are going to hit that coincidence detector marked in X at the same time. So if that coincidence detector is getting input from the delay gate and retinal ganglion cell B simultaneously, that causes it to fire. So if the timing works such that the action potential from the delay gate reaches the coincidence detector X at the same time as the action potential from retinal ganglion cell B, it causes a cell in V5 to fire. So what this means is that these delay gates are wired up continuously throughout the brain with different timing delays to enable us to detect multiple directions of motion and speeds of motion. But what's interesting about this system is that it doesn't require actual real motion in order to activate it. So because of the way that V5 is wired up, we perceive motion when we see something in one location that then quickly moves to another location. Now, normally in the real world, objects move continuously through intermediate stages, but we can also perceive motion when objects rapidly disappear from one location and then reappear in another location. This is known as apparent motion. It's the illusory impression of smooth motion that results from rapid alternation of objects in different locations. So, this neural circuitry doesn't need real motion in order to fire. It just needs something to be here and then something to be here at precisely the right time, but it doesn't really need anything to happen in between in order for us to perceive motion. And we make sense of apparent motion all the time. In fact, you're doing it right now. This video is recorded at 30 frames per second, meaning every second you're seeing 30 different still images of me. You're not seeing me moving. You're seeing still pictures of me. But it's a rapid enough change that the motion sensing circuitry in your brain is interpreting that as motion. I'm not moving. I'm moving, but you're not seeing me move. You're just seeing still pictures of me. I'm not even moving. Check it out. It's just still images. All right, here's another nice demonstration. Okay, this is just two still images of hands in different configurations, right? I'm just flipping back and forth between them. But if you show this to people, they will often report that they think they saw the hand at some intermediate position, right? They think it didn't just go from this to this. They think they actually saw this. Check it out. Right? You kind of feel like you can see those intermediate stages. But what is seeing those intermediate stages is not your photoreceptors. No, that is perceptual fill-in that's coming from top-down sources, right? That's your brain that's doing that. The Lilac chaser illusion that you watched is another lovely example of apparent motion. You really get the impression that the dot is running around the circle, when in fact the dots are just taking turns blinking off. Another wonderful demonstration of apparent motion is this great train Jiff. Which way is the train moving? Is it coming towards us or is it going into the tunnel? Once you see it one way, try to force it to go the other way. And a good way of doing that is by looking either at the tunnel or looking at the train kind of where it is closer to us. Most people report that they can make it appear to move in both directions. So what's happening? How can this possibly work? Now, if we were to imagine it going away, there is this one point on the train here, now becomes this point, now becomes this point, now becomes this point. If you were to imagine it coming toward us, then this point, then becomes this point, then becomes this point, then becomes this point. So this is a case where we have a bistable motion effect. It's like phase-vase, it's like the tritone paradox. There's information consistent with both interpretations because we have a pattern that repeats in a way that is consistent with either interpretation. So just as in the tritone paradox, where some of the frequencies go up and some of the frequencies go down, in this case, there is visual information that is consistent with both the train moving away and the train coming closer to us. So motion perception depends on the real or implied motion of objects, and we do our best to interpret that despite the fact that the input is so ambiguous. Now it's time for us to bust a move toward the problem set. Okay, so these are the locations of 3 hypothetical injuries. The idea is that no visual information can get past the place where the line is. So what you're figuring out is how perception from each eye and perception overall would be affected if there were stroke or some other kind of injury that caused localized damage at A, B, and C. Okay, so if we have a slice basically at the optic nerve of the right eye, it means that everything from the left eye reaches cortex. Nothing from the right eye reaches cortex. And so the overall perception is of everything except the portion of visual field that is only coded for by the right eye. And that is just the far, far periphery, right? That is just way, way out here. If an injury were to happen at the optic chiasm, the information from the left visual field of the left eye is lost, right? That's the part from the left eye that is in blue, so the part that goes contralateral. From the right eye, information about the right visual field is lost. So that's what's shown coming from the right eye in red. That's everything that moves contralaterally from the right eye. And so what that means is that you will see everything except the information that is coded uniquely by each eye. So except for point 1 on the schematic that only the left eye can see, and point 9 on the schematic that only the right eye can see. And finally, if you have damage at the optic radiations, which are in between thalamus and V1, it means that all of the information from the right visual field is lost for both eyes. So because the information has gone from the right visual field to left visual cortex, and that is true of both eyes, it means that you have lost all of the information about the right visual field. So that means that the right visual field is completely lost. As you go from eye to brain, the same amount of damage has more dramatic results, right? You can lose visual information from a whole eye, and you don't lose very much about visual perception. But if you lose that, if you have damage of that same scale in the brain, it's going to cause a lot more damage. Nope. Blindsight would not work if they're wearing a blindfold. The visual information still has to get into the brain somehow. So Blindsight only happens when there's damage to V1, but the rest of the visual pathway is intact. So for instance, someone who is blind because of damage sustained to the eyes or to the optic nerve couldn't possibly have blind sight because that information, that visual information, needs some way of making it into the brain. All right, so what causes these delightful motion after effects? Well, we know that if all of the cells are responding equally, if there is no motion, that indicates that there is no motion. If you stare at one direction of motion for a long time, you get fatigue, you get adaptation of neurons in the columns that code for the direction of the motion that you were perceiving. So if you're staring at something that is moving leftward for a long time, you get fatigue or adaptation in the leftward sensing direction selective columns in V5, and that results in an imbalanced response. So then when you go to stare at something that is not moving, something that's stationary, you're not getting the kind of response that you typically would. You're getting the kind of response that you typically would minus the input from those leftward sensitive direction selective cells. So that makes things appear to drift rightward. If you have activity in the upward motion circuit and the downward motion circuit simultaneously, those in effect cancel each other out. But here, the activation in the rightward motion circuit is stronger than the activation in the leftward motion circuit. So when you stare at something going to the left for a long time, you then perceive an after image moving to the right. And because these effects are happening in cortical circuits in the brain, it's not eye specific, this means that you do get some interocular transfer. That is, if you stare at something moving to the left with your left eye, and then look at something stationary with your right eye, you still get some of that motion after effect. It's not as strong as if you stare with both eyes, because then you're getting more input from both eyes and causing more fatigue, but you still do get some transfer from one eye to the other. So in some ways, this is similar to color after images, right? You stare at blue, then you see yellow. You stare at leftward motion, then you see rightward motion. But a difference between motion after images and color after images is that you will not get interocular transfer with color after images, because the cause of color after images is the Because the cause of color after images is that the specific photopigments associated with the wavelengths that are present isomerize, get bleached, the supply of that photoreceptor gets exhausted. So that whole process is happening in the eye. So the things that are adapting and the after image that occurs as a result is happening within the eye. But with motion after effects, the things that are fatiguing are happening in the brain, right? They're happening in V5. Cool, right? All right, that's it for today.